Standard machine learning design maintains a strict wall between training and inference. A model first learns in a controlled environment, and only then is it deployed to execute its task. Within this framework, an operational error is a terminal event. When the network fails, the system must recalculate, relying on global processes like backpropagation to adjust weights across the entire structure. Aurora treats the error state, labeled E equals 2, as an operational signal. This state indicates an open ring, triggering the node to expand its visual radius and capture adjacent nodes to gain necessary context. By removing the need for massive training cycles, Aurora functions as a distributed, asynchronous system driven entirely by events. Every adjustment in the network follows a cascade toward geometric coherence, setting the stage for a system where reasoning and learning share the same underlying mechanics. Aurora operates as a unified mathematical substrate that manifests differently across 4 distinct scales of observation. These 4 levels of resolution range from the logic gate at level 1 and the constraint graph at level 2 to the geometric topology of level 3 and the neural network of level 4. Across these scales, the architecture functions without a central planner or a master clock to dictate the order of execution. Without a central authority to direct the calculation, the system's output emerges only when the entire structure achieves a perfect geometric closure. The atomic unit of this substrate is the Trigate. While a classical logic gate is a one-way function designed to calculate an output, the Trigate is a reversible mathematical constraint. It operates on a ternary domain, 0, 1, and 2. The value of 2 represents a state of openness or the unknown, rather than a logical failure. A control variable, c, dictates the direction of the resolution. Changing this variable reverses the directional flow of the mathematical relationship without altering the underlying connections of the nodes. This reversibility allows the same atomic unit to learn, infer, or deduce, depending on its orientation. The system simply evaluates the same constraint from different directions. When a Trigate detects a local contradiction, it preserves that state. This conflict becomes a signal that travels through the substrate to find contextual redundancy. At this purely deterministic level, the system evaluates possible domains, reduces constraints, and requests more data when the logical pieces do not align. Zooming out reveals a vast interconnected web. This is a Kara. At level 2, the base logic transforms into a constraint satisfaction problem. Each Kara processes 3 input vectors, or coordinates, operating within a specific reference space. These coordinates enter a distillation stage. A specialized node synthesizes the raw input into 3 clear operational dimensions. The system then measures geometric emergence. It calculates the exact deviation of these dimensions, checking how close the vectors are to forming a perfect equilateral triangle in their reference space. If the dimensions fit that equilateral triangle, the Kara achieves geometric closure, producing a 0-0-0 state. At this point, the information crystallizes and the reconstructive knowledge is consolidated. If the vectors fail to close, the Kara emits a carry event. It asynchronously requests additional tensors from the network to expand its window and retry the process with more context. Level 2 turns the logic of domains into a problem of physical stability. Reasoning is the reduction of constraints until the geometry stabilizes. When the constraint graph freezes into stable shapes, we reach level 3, the Transcender. This is a topology built from 7 interlocking equilateral triangles, or Karas. Specific mathematical roles are assigned within this topology. Kara 4 evaluates the ideal search direction, Kara 5 audits global coherence, and Kara 6 calculates how to minimize the operational cost. These specialized measurements feed into the unifying decision organ of the structure, Kara 7. Kara 7 operates without pre-programmed thresholds or external control. Its resolutions are purely relative, based entirely on the current geometric state of the components. To dictate the system's behavior, Kara 7 calculates 3 simultaneous independent differentials: the distance of direction, the distance of coherence, and the distance of cost. By evaluating these 3 differentials together, the architecture determines which variables to adjust to minimize the Manhattan distance and pull the entire topology toward equilateral closure. At this level, Aurora is pure topology, measuring shapes, distance metrics, and closure angles. AI understanding becomes an act of spatial alignment. An extreme pullback to level 4 reveals the macroscopic behavior. Hundreds of transcenders work in parallel, operating simultaneously on a massive cluster of tensors. To organize this density of operations, Aurora uses its dictionary. This is not a static table of text equivalencies. The dictionary is a living record of coherence crystals. Each entry is a fractal tensor, nested triangles that achieved mathematically perfect closure in the past. These crystals compete to stay in the operational record. The system assigns priority based on length, recency, and how often they contribute to successful closures. If a crystal loses its coherent utility, it cools and is displaced from the main cascade. Throughout the macroscopic structure, domain reductions trigger events that propagate asynchronously from node to node, without hierarchical oversight. The collective behavior at the scale mimics a classical neural network. However, learning is simply the structural residue left behind as the network consolidates the most stable crystals. The architecture rests on an invariant. Each level geometrically aggregates the one below it. A simple logic contradiction in a lower Trigate forces spatial reconfiguration in the middle layer's triangles. This immediately transmits a massive reorganization wave through the asynchronous cluster above. Because every level reacts to continuous constraints, Aurora lacks an isolated execution stage where weights are frozen. The network does not force a linear calculation. The response arises through dynamic equilibrium, achieved the moment the cascade stops its motion and hits equilateral closures. When generating output, the expansion network does not invent new forms. It strictly retrieves fractal tensors already existing as consolidated structures in the dictionary. This reliance on consolidated crystals requires an external stabilizing force to prevent structural drift. The system solves this by designating the user as its oracle. The user anchors the system by injecting tokens into the dictionary. This input introduces priority, acting as a gravitational anchor that pulls the asynchronous cascade toward a specific operational direction. Because of this massive gravitational effect on the geometry, everyday interaction and correction are mathematically the exact same act. Aurora moves AI intelligence away from traditional statistical loss functions. It proves that a cognitive network does not need to be numerically forced if it operates as a dynamic system, converging toward the geometric coherence dictated by its oracle.